Okay, so we've found and depicted a point on the graph of this function corresponding to x equals 4, y equals 9, the point being 4, 9, 7. We've sketched an indication of the behavior as we move in the y direction from this point. And we see that we have a slight change in y, a change of 0.03 in y when x changes by 0.2. Here we have a change of 0.1 in y when when x changes by 0.2. This happens when y changes by 0.2, from 9 to 9.2. As x changes from 4 to 4.1, from here to here, the y value changes by 0.1, and that happens over a distance of 0.1, whereas the change 0.03 happens over distance 0.02. We can say that the slope in the YZ plane of this segment is 0.03 over 0.2 is 0.15. Means if we're on the surface of this graph moving in the y direction at this point, we're going to be going up a slope of 0.15. And incidentally, the slope of this segment here is clearly less than 0.15, but remember, we're not really drawing things to scale. This is just a schematic indicating the nature of what happens. Okay, if we go in this direction, then we're moving in the x direction from this point. We're moving 0.1 unit and up 0.1 units. So we're moving up at a 45-degree angle. You can't really walk on that, so it's very steep. And the slope here is, of course, then, if we're moving the same distance in the x direction we are in the z direction, the slope is 1. What we really want in order to get tangent lines is we want vectors. We want a vector in this direction and a vector in this direction, because we know that if we have two vectors in our tangent plane and a point on the two vectors tangent to the plane at a given point, then we get the normal vector by taking the cross product of our vectors, and we got a point on the plane. We can easily find the equation of the plane. Okay, so let's just postulate a vector somewhere in this direction. Now, it might be longer than this, it might be shorter than this. This just indicates a general vector that I'll call V. And similarly, a general vector that I'll call U in this direction. So this vector V is in the YZ plane, in a plane parallel to the YZ plane that goes through the point 490. This one is in a plane parallel to the XZ plane, but through the point 490. What are possible vectors here and here? Well, for the V vector, one easy way to get a vector is just to do a vector from this point to this point. Now, that's not how I drew this vector. This vector is just a schematic representing any possible vector in this direction. So we could use the vector from here to here. It would terminate right here. And that vector would be, well, 0.2 units in the y direction, which is 2.2j, the displacement 0.2j, and 0.03 in the z or the k direction. Okay, so we have our 0.03k. So the vector 0.2j plus 0.03k is a perfectly good vector to use here. Or we could use, we've calculated the slope. We've calculated the slope of this thing. It's 0.15. Well, if we go 1 unit in the y direction, corresponding to displacement along the vector j, 1j, then what's the rise going to be? That's the run. The rise is going to be what? If the slope is 0.15 and the run is 1, then the rise had better be what? 0.15, because rise divided by run equals slope. So rise of 0.1 divided by a run of 1 gives us a slope of 0.15. Okay, well, now we have then the vector j plus 1.5k. So this is easy if the slope is known. This is easy from the given information. We might also want a unit vector for one reason or another. We could base a unit vector on our first vector, the magnitude of this vector being the sum of the squares of the two components, and the original vector divided by that magnitude. Magnitude of this vector is clearly 0.1 plus 0.15 squared, so we divide the vector by the magnitude. These vectors are equal. They don't look the same, but if we work out the numbers, the actual coefficient of j, the exact coefficient of j is going to be the same in both cases, as will the coefficient of k. So we'll note that those unit vectors are just two different ways of writing the same unit vector. Similarly, the vector u could be, well, we go 0.1 in the I direction and 0.1 in the k direction, and we get 0.1i plus 0.1k. Of course, if we multiply both of these by 10, we get I plus k. Or, alternatively, if we say, well, I want to go 1 unit in the direction of I, so I'll have I here. Since the rise is equal to the run, the slope is 1, then our rise has to be equal to the run. If I use I, the run is 1, so that the rise must be 1, so that the coefficient of k has to be 1. And we could write the corresponding unit vectors. Again, these are identical. They just look a little different. Okay, so now we've got a vector v and a vector u, both tangent to the curve. So I'll say both u and v, tangent, I said, to the curve, to the surface, at the point 4, 9, 7. Now we can proceed easily to get the normal plane. We just take the cross product of the two vectors. If we want a unit vector normal, we divide by the magnitude of that cross product. And I've kind of indicated the product. And I chose to do the unit vectors, okay? I used the j plus 0.15k from here divided by its magnitude, and the I plus k divided by its magnitude here. Now, I do that cross product, and then I've got to divide by the magnitude of the cross product. I didn't write all that out. Over here, I did the cross product of the numerators. Comes out very straightforward. And I included the product of the denominators. And now, if I want the unit normal, I'm going to have to divide by the magnitude of this, which is a little bit complicated, not too bad, but I'm going to have to write out that magnitude in the denominator. Then I'll have a complex fraction. I'll have to simplify it, but I'll get some multiple of I, some multiple of j, some multiple of k. If I prefer, I could just use I plus 0.15j minus k as my normal vector if I didn't want to have any reason to need a unit normal vector. One way or the other, I've got a normal vector and I've got a point 497. Now I can find the surface. So the plane through 497 with normal vector n as calculated here.